Hello third year, welcome to this video looking at formula and recapping the formula rules that we learned in Unit 1. So the basics of formula then. We know that elements and compounds can form different structures. Okay, we learned the different structures in Unit 1 when we were learning about bonding. And the basic structures would be covalent molecules. So we've got ammonia, an example here, we've got nitrogen bonded to 3 hydrogens, and we've got hydrogen, which is an example of a diatomic element, and we've got water, where we've got an oxygen, which is bonded to 2 hydrogens. We can also get covalent networks, and these are where there's a giant network of atoms that could be the same type or different, but in this example, it's silicon dioxide, so we can see the silicon atoms represented like so, and the oxygen atoms represented like so. And what happens is this shape builds up to give this sort of structure, which continues on in a giant, seemingly infinite, although obviously it does end, structure where we've got millions and millions and millions of atoms in the structure. And finally, we've got ionic lattice. Now, ionic lattice consists of oppositely charged ions. In this case, we've got chloride ions, which are negative, and sodium ions, which are positive. And they are attracted to each other, and then they're held together by ionic bonds in a crystal structure, which we call a lattice. Okay, so those are 3 basic structures of compounds. And chemical formula is a way of representing either the number of atoms in a covalent molecule, so counting that number of atoms. It could also be the ratio of atoms in a covalent network. So for example, in the silicon dioxide, we had 1 silicon for every 2 oxygens. So it would be SiO2. Or it could be the ratio of ions in an ionic compound. So in our sodium chloride, we had 1 sodium ion for every 1 chloride ion. So that's a 1-to-1 ratio, so it would be NaCl. Okay, so the way we work out formula doesn't depend on what type of substance it is, but the formula means slightly different things depending on what substance it is. Okay, so that's just a recap of what formula is. We're going to look at the different types of formula that we might be asked for then. So firstly, we've got formula for elements. Okay, so you could be asked for the formula of any element in the periodic table. For almost all of them, the formula would just be the symbol, but the exception is the diatomic element. You could be asked for the basic formula of compounds. At S3, we're only looking at 2-element compounds. But you could have a 2-element compound where you've got a transition metal, and you would know that because there would be Roman numerals in the name. You could be asked for the ionic formula of a 2-element compound where you need to give the charges. And then you could also be asked for the formula for a compound where the name includes prefixes. Okay, so that's a little bit that comes before part of the name, mono, di, tri, tetra, and so on, that is going to indicate the number of each type of atom. We're going to go through each of these types of formula in turn, and I'm just going to give you some examples of what it looks like. For almost all types of formula, we use the SVSDF method to get from the name to the formula. Okay, so this is the key part that we need to sort of remember, and it's the main tool that we're going to use to be able to write formula. So S is for symbol, where we write the symbol for the element. V is where we write the valency for that element. So remember, valency is the combining power that relates to the number of unpaired electrons that element has in its outer shell. Then we swap over the valencies if they're different, and if we can, we divide them to give the simplest ratio, and then we write out the formula. Okay, so let's do some examples here. Firstly, let's think about the element copper. Okay, so if we were asked for the formula for copper, we would just look in our data booklet and we would see the symbol is Cu. So the formula is just Cu. Chlorine is another element. Chlorine has the symbol Cl, but chlorine is one of the diatomic elements, so we need to put that little 2 in. The other diatomic elements include hydrogen, oxygen, nitrogen, and the other group 7 elements, but specifically fluorine, chlorine that's in this question, bromine, and iodine, okay? You need to know which elements are diatomic, okay? So you need to memorize that. Okay, so for elements, it's just the symbol, unless it's diatomic, it's HON or one of the halogens, and then in that case you would write the little subscript 2. Okay, so looking at some of the 2-element compounds that we need to know. So I know that I'm going to have to use SVSDF in these ones, okay? So that's my technique. So to answer this question then, I'm going to write out all the different parts of this formula. So the symbol then for sodium is Na. Sodium's in group 1 in the periodic table. And for oxygen, it's O. Then underneath them, I write their valencies. So the valency for sodium is 1 because it's in group 1, and for oxygen is 2 because it's in group 6. So remember, the valencies go 1, 2, 3, 4 in groups 1, 2, 3, 4. And then in group 5, it's 3, group 6, it's 2, group 7, it's 1, and group 8, it's 0. Then we swap over the valencies if they're different. In this case, they are 2 and 1. And then we can't divide them to get any simpler ratio. So the ratio is then 2 to 1. So that means the formula would be Na2O. So there's 2 sodiums and 1 oxygen. So we don't need to put a 1 in there because obviously there must be at least 1, otherwise we wouldn't have written the symbol. So if there's only 1, then we don't write the number in. It's only if it's a number that's greater than 1. Okay, this one is barium phosphide. So again, we're going to use SVSDF. Okay, so barium is Ba and phosphorus is P. Barium in group 2 has a valency of 2. Phosphorus in group 5 has a valency of 3. We cross them over and we can't divide them into anything simpler. So it's going to be Ba3P2. This one is lithium bromide. So we've got SVSDF. Lithium is Li, bromine is Br. Valencies are both 1. So if the valencies are the same, then we can just skip to the formula stage and write LiBr, because swapping them is not going to change it, and then dividing them, if they're already 1, is still going to be 1. Okay, so that's going to be LiBr. Okay, aluminium sulfide, so SVSDF, Al for aluminium and S for sulfur. Aluminium's valency is 3 and sulfur's is 2. We swap them over, 2 and 3. Can't divide them into anything simpler, so that'll be Al2S3. Our next example has a Roman numeral here, so that's a Roman number 2. So the Roman numerals, remember, we've got 1, 2, 3, 4, 5, 6. That's really the ones that we need to know about. And we need to be given the Roman numeral because this element, iron, is a transition metal. The elements that are between groups 2 and 3 in the periodic table can have different valency. They can have more than one valency. So you need to be told what their valency is in the name. So we just construct our SVSDF as normal, except at this stage, when it comes to doing the valency, instead of looking in our data book at what group it's in, we look at the name. Okay, so iron is Fe, nitrogen is N, valencies are 2 and 3, swap them, 3, 2, can't divide them into anything simpler, so Fe3N, 2. Manganese 4 oxide. Okay, so we've got SVSDF. Manganese is Mn. Oxygen is O. Valency for the manganese, this represents 1 before 5, so that's 4. And then oxygen is 2. Swap them to get 2 and 4. We can divide this down to be 1 and 2. And so the formula would be MnO2. Okay, so now we've got to give the ionic formula for this one. So I'm going to show you just to work out the normal formula and then add in the charges at the last step, because we'll already have all the information we need to work out what the charges are. So potassium fluoride, SVSDF, so we've got KF where the valencies are 1 and 1, so it's just KF. And because they've both got a valency of 1, then they'll both have a single charge. The potassium, because it's a metal, it loses electrons to become positively charged. And the fluorine, it's a non-metal, so to become a fluoride ion, it gains that electron from the potassium. So the ionic formula is going to look like this. So K plus F minus. And remember, the charges are superscript. They appear at the top of the text. Okay, so K plus F minus. Because we only have one of each of the ions, then there's no requirement to put any brackets in. Okay, this one here is magnesium iodide. So let's go. It's another ionic one. So we've got SVSDF, Mg and I. So valencies are 2 and 1. Swap them, and then MgI2. And then the magnesium, it's the metal and it's got a 2 positive charge. And the iodide, it's a non-metal and it's got a 1 negative charge. So it's going to be Mg2 plus I minus, but I've got 2 of them, okay? So anytime that I've got a number subscript at the bottom of the line indicating that I've got more than one of the ion, then I need to put in brackets, and that just helps to organise the formula so you can see clearly where the charge is and where the number is. Okay. This one, I think, is supposed to be ionic too, so we'll do this one ionically as well. This is lead to chloride. So we've got lead, let's just stick to the right colour pen. SVSDF. Okay, so lead is Pb and chlorine is Cl. The valency of lead is 2, chlorine is 1. Swap them over, can't divide them any further, so it's going to be PbCl2. And then again, so the valency of the lead is going to be 2 positive, and the valency of the chloride is going to be 1 negative, and I've got 2 of those. So Pb 2 plus Cl minus, all in brackets, 2. Okay, the final type of formula we need to do is the type with prefixes. That's when we have mono, di, tri, tetra, tetra, penta, hexa, hepta, and octa. And those tell us how many of the atom there are in the formula. When we see prefixes, we do not use the SVSDF method for working out formula. We just write down from the name how many of each type of atom there are. And if there is no prefix, then it is 1. Okay, sometimes the prefix mono is also given, but whether it's mono or there's no prefix, then it would be 1, and any other prefix would indicate the number. So here we've got no prefix here for the boron, so that must be 1 boron, and tri for the chloride. So the formula for this one would be boron, which is B, and then 3 chlorines. So boron, trichloride. This one here, vanadium pentoxide. So vanadium is V, and pent, this prefix means 5. So that means I'm going to have 5 oxygens. No using SVSDF, no working at valencies, just from the name. Okay, and this one I've got dinitrogen tetroxide. So di for 2 and tet for 4. So I'm going to write down N2O4. Now, what's important to know is that if we're given prefixes, then even though this could be simplified down into a 1:2 ratio, we don't do that. When you're given the prefixes, you leave the ratio whatever it is and you don't do any simplifying. So N2O4 is the correct answer for this. Okay, the very final and quick part of this lesson then is just quickly recapping what relative atomic mass is. So the mass of an atom is made up of its protons and its neutrons. Now, an atom will also have electrons, but their mass is negligible. That means we don't count it towards the total mass. Atoms of the same element can exist with different numbers of neutrons. They are called isotopes. So isotopes refer to same element, different numbers of neutrons. So they'll have the same atomic number, but different mass numbers. So they will have different masses. The relative atomic mass, or RAM, or RAM, of an element is the average mass of all the atoms or isotopes of that particular element. And you can find all of the relative atomic masses of the elements in the periodic table on page 7 of your data booklet. Okay, hopefully you managed to keep up okay with this recap on formula, and let me know if you have any questions and I'll be happy to help. Thanks.